Here we go. Okay, today we're going to be talking about energy. So, grab a color over here. So, energy. In your books, it talks about all sorts of different kinds of energy, and there are a few mistakes in your book. So we will see what we can do about that. But we get all sorts of different kinds of energy, and the names that we give to energy depends on what they do or where they come from. Okay, so the first thing I'm going to talk about is energy coming from movement or being caused by movement. So that is our broad category. So now let's go into the slight more details. Okay, so our first kind of energy that can be caused by movement is gravitational potential energy. So it is a bit of a mouthful. So if I have to break this down, this is essentially the potential that something has to release some energy due to gravity. So I'm going to put an equation here. You guys don't need to know the equation. I just want to explain it a bit. So this E is the energy. This M is the mass of an object in kilograms. G is our gravity. And H is how high we put the object. So if we have a table or a wall or something, and we are going to put an object over here. So how heavy this object is will mean that it can fall faster and actually hit the ground harder over here. So gravity tries to pull this object down. And how high we put the object is also going to contribute to how hard it can essentially hit the ground. How big it is can also affect how hard it can hit the ground. So this rock that we put up here in a very precarious position essentially has the potential of falling down and hitting the ground very hard. So that is what we call gravitational potential energy. So if it falls, it will then convert all of the energy it had stored from being up there into essentially movement, into kinetic energy. So that brings us to the next kind, which is kinetic energy. So kinetic energy is the energy that is caused due to something moving. Okay, so I'm going to give you guys a fairly easy example. So let's draw a pool table over here. You guys have probably all seen a pool table at some point. So here we have a very rough sketch of a pool table. And here we have our ball. One of those snooker balls, pool balls, whatever. It's going to be hit and it's going to travel in this direction. Over here, we've got another ball. So this one is going to hit this one. So this ball has some energy due to the fact that it is busy moving in a direction. When it hits this ball, what's going to happen is essentially this ball is going to start coming back, and this ball is essentially going to travel forward with some kind of movement as well. So this ball has then given some of its kinetic energy over to this ball over here, causing it to move. So this is what I mean with kinetic energy. It is the energy something has due to the fact that it is busy moving. Okay, so you transfer kinetic energy when two things collide with each other. So if we have some kind of collision, here we've got a collision between two pool balls. If we have any other kind of collision between two cars, means all of that movement that it had, the kinetic energy will then be transferred into essentially crunching up the cars or hurting the people inside. So this is what I mean with kinetic energy. So the next kind of energy due to movement is called elastic potential energy. Okay, so just like we had gravitational potential energy, elastic potential energy is the energy we have due to the fact that some kind of spring or elastic is acting upon the object. So this is the energy stored in a spring. Or a rubber band or any other kind of things that can essentially store energy in such ways. In your books, this is called strain energy, but that is not a very good term to use for it. So I do not use strain energy. That is actually a terrible name for this, due to the fact that strain is literally just the force that is put on something in a specific way. So strain energy doesn't quite work so well. Okay, so essentially what happens is if we've got a spring over here and we compress that spring, so we push it down, then when we let that spring go, it will essentially bounce up, releasing that energy that we put in. Okay, so this is elastic potential energy. It is the energy something has due to it being in some form elastic. So if we have a spring, we can squish it and it'll let go again. We can use rubber bands. If you think about bungee jumpers, that is literally energy being stored in some rubber bands, very thick, nice rubber bands. So yeah. So that is that kind of energy. Now we get to the energy from vibrations. Okay. Your books call this sound energy. That is an absolutely terrible name for it. Please don't use the name sound energy. I'm just going to write it in brackets over here so that you guys can remember what it's being called in your books. But it is not the sound that is the energy. It's the vibrations that is carrying the energy. So this is literally energy from vibrations. That can be a loud sound that breaks windows. If you've ever heard of a shock wave, that is an energy coming from some kind of vibrations. It could also be something like breaking a wine glass using your voice. If you've ever seen opera singers do that trick, it's quite cool. So this is essentially what your books call sound energy, but yeah. So this is loud sounds, breaking windows. Shock waves. Technically, earthquakes are also a kind of energy that is used with vibrations. So this category does not just cover sound. This category covers a whole big broad spectrum of things, but it is the energy being carried in something that vibrates. Normally it's the air. In terms of earthquakes, it can be the actual earth that vibrates. Shock waves can cause things like tsunamis, so that is the water that is carrying the vibration. So it literally depends upon our mediums. So that is all of the different kinds of energy that we get due to movement. So now we're moving on to chemical energy. There was a question. I will see if we have enough time afterwards to see a video of an opera singer breaking a wine glass, but we shall see. So here we've got 3 different categories. So the first category is essentially energy stored in food. Your body can take the energy that is being stored in food during digestion and then convert it into energy your body can actually use in order to move. So this is a kind of chemical energy. Yes, it is calories. This energy you normally see on the backs of whatever containers your food comes in, and it is measured in kilojoules. That is the energy content of food. So that's one kind of chemical energy. Another chemical energy is the energy stored in batteries. I believe your book some way puts this under the electrical category. It's not. The energy inside of a battery is literally due to the fact that you have 2 different substances stored inside the battery. And when you connect an external circuit to it, then those 2 substances can react with each other and let go of that stored energy into the circuit, which then powers your light bulbs and things. So we've got energy stored in batteries. This is a chemical energy. Okay. The last kind is energy from chemicals reacting, which sounds kind of strange when I just talked about batteries. This is just literally any 2 chemicals that we have reacting in some way we can get energy from. So okay, so this one, we can have a few different ways that the chemicals can release this energy. So the first kind, which your book talks about quite a bit, is exothermic reactions. So a reaction that lets heat off is called an exothermic reaction. Okay, and the other way it can release energy is in the form of pressure from gases. So the 2 chemicals will react, and one of the resultant things will be a gas that it lets off, and then you end up with pressure building up due to this gas. A very, very quick and easy example of this is if you guys have ever seen someone put Mentos in a bottle of Coke or Cola. Just literally putting that Mentos in makes the whole thing just like sort of explode. There is cool drink flowing absolutely everywhere. If you actually screw on the top of the bottle before doing that and run away very quickly, it'll explode. There's lots of energy coming from this kinds of things. So yeah, that is our different kinds of chemical energies. And I did read that you guys said nuclear energy. Nuclear energy is in a separate category, so I will get to that one. So here we go. Then we get electrical energy. So this is essentially the energy we use when we plug something into a wall or put it in a circuit with a battery or something like that. So here I want to highlight the term voltage. So voltage in actual terms, if you go look it up, it'll be a potential difference between 2 points in a circuit. So if we have something that uses a certain amount of volts of electricity, that is literally the sort of potential something electrical has to do things. So things have to do things. This is put in very, very basic terms. So I am not going to go too much into detail here. Electrical energy we tend to measure in volts. So if you have a 2-volt battery, that is essentially how much power that battery can supply to the circuit. It can run things of that can run off of 2 volts worth of power. So yeah. So next up, we have heat energy. So heat energy, we've got 2 categories. Okay, so the first kind we have is radiating heat. So this is if you're standing in front of a heater and you feel the heat coming off of it. This is essentially what we mean. The heat from your stove that you use to cook your food. This is essentially that kind of heat energy. So we've got radiating heat. So I'm just going to put a stove in here so you guys understand. The other kind of heat energy we have is called internal energy. So this one is a little hard to understand, so bear with me. Internal energy is the energy the particles inside of a substance has. So here we have particles. Okay. You guys probably remember these kinds of sketches where you had to draw a solid and it had all of these particles sort of densely packed like that. And then you had a liquid where you had the particles sort of more slightly looser and they can sort of move past each other in some ways and things like that. So yes, this is basically the particles inside of a substance's energies. So we call this the internal energy of something. It's literally all of the energy of the particles inside it. And then if we have a gas, these particles are literally busy moving around in all sorts of ways. Okay, so that is what we mean with internal energy. It's the energy that the particles inside of a substance has. So it is also a kind of heat energy, since if you're heating up a substance, that substance is not necessarily giving off the heat, so it's not a radiating heat energy, but it absorbs that sort of heat energy that you give, and that causes the particles inside to vibrate harder or to move quicker or something like that. So that is what we mean with internal energy. Okay, next up we have electromagnetic energy. Okay, electromagnetic energy is energy coming from electromagnetic waves. So this includes everything from radio waves to microwaves. I'm not going to write the word waves out every single time, it takes too long. Infrared, visible light, ultraviolet, so UV light coming from the sun, this is part of this sort of thing, X-rays, and gamma rays. This is all in this category. So I have arranged them here in terms of the least energy, increasing all the way to over here with the most energy. Okay, so I see you guys haven't heard of gamma rays before. So essentially what gamma rays are, they are specific kinds of light that we can't see, but they have very, very high energy, and they're actually very dangerous. Coming from things that give off tons of energy, like a supernova in space gives off gamma rays. It is ridiculously high energy rays. You guys already know that X-rays, if you have too much X-rays going through you at any one time, it can actually cause quite a bit of damage. It can cause cancer cells to develop, all sorts of things like that. Gamma rays do essentially the same. It's just higher energy than X-rays are. So X-rays don't go through your bones, but it goes through everything else in your body. And that's why we can use X-rays to look at what your bones look like inside of your body. But gamma rays just go straight through pretty much everything. It goes straight through your bones. It goes straight through everything. It is just ridiculously high energy electromagnetic waves. Okay, so pretty much most of the energy in the universe is comprised in this little bit here, from radio waves all the way through to gamma rays. Heat, all of that radiating heat energy, that is essentially infrared radiation. In your books, you've got this being called light energy. So you've got light energy. That made me cringe so hard when I read that. So light energy, essentially what your book calls light energy is this little bit here. All of these, from radio waves all the way down to gamma rays, is a form of light. The only light that we can actually see is this bit here, visible light. Everything else is also a form of light. We just can't necessarily see it. So if you look at astronomy, there are actually telescopes ranging right across the spectrum. There are radio telescopes that they use to look at the light coming in radio wave form. There are microwave telescopes. There are infrared telescopes. There's normal telescopes that you can use to look at visible light. There are X-ray telescopes, but for X-ray telescopes, we actually have to send up satellites into space due to the fact that the atmosphere actually blocks quite a lot of X-rays. So we don't actually see that very often. We actually have to put all of our equipment in space in order to see X-rays and gamma rays and things like that. We have telescopes that can look at these. They're just in space. So this electromagnetic energy is probably the most important thing for astronomy. All of the information we have about the universe, about all of the stars out there, about all of the planets, we got in terms of all of these. That's it, electromagnetic energy. So that's that one. And now we get to our last kind of energy, the one you guys have been waiting for, nuclear energy. Okay, so there are three kinds of nuclear energy. There's fission, fusion, and then there are energy coming from subatomic particles. Okay, so let me just start here. Nuclear fission, right? That is what you guys know as nuclear power. Nuclear power stations use fission. Essentially what that means is they take a particle of uranium, they shoot a neutron at it, which causes this particle to split into two parts, which is actually krypton and barium. It splits into two parts, krypton and barium. Those are then radioactive, which falls under this category over here. So it's a bit broad. So fission is what is used with nuclear bombs, nuclear power stations, all of these kinds of things. That is fission. Okay. In terms of things like aircraft carriers, submarines that have nuclear power on board, they've got a very tiny nuclear power station on board. That is what they mean. Okay, then we have nuclear fusion. So this is a special kind of energy that we get, and this is essentially the sun. It is the closest thing we have that actually does this. All stars have nuclear fusion happening. So this is when we take hydrogen and it combines hydrogen atoms and things together in certain ways to form helium. And it gives off quite a lot of energy doing this. So this is the sun. So we've got fission, which is nuclear bombs, power stations, fusion, which is the sun. So now we get to the ones due to subatomic particles. So subatomic particles are protons, neutrons, electrons, and other subatomic particles like quarks. You guys have probably heard in the last few years about something called the Higgs boson. That's also subatomic particles. It's literally the sort of things that little particles inside atoms are being made of. Okay, so here we've got something happening, which is called radioactive decay. Okay, so firstly, this sounds remarkably dangerous. Radioactive decay is actually a fairly natural thing occurring. The bones inside of your body is busy undergoing radioactive decay at this point in time. It's literally happening. It is not dangerous in small quantities. We measure radioactive decay using something called a Geiger counter. So when radioactive decay becomes dangerous is when it is happening very, very quickly. We use radioactive decay actually in things like carbon dating to see how old things are, like dinosaur bones and all sorts of things. So this is a kind of energy that we get from subatomic particles turning into different kinds of subatomic particles. And this mainly happens with quarks. So I am not going to explain how this works. It took me 6 months in university to realize how this works. So I'm not going to explain it. I just want you guys to know that it is there. Okay. So now, what do you guys actually need to know? You guys need to know the different kinds of energy you can get and some examples of each of them. You don't need to know all of the examples, just some of them. And you don't need to know about nuclear energy. It is not in your books at all. I just wanted to put it there because I like to be complete. And you guys have definitely been asking about nuclear energy.